Hi, and welcome to this video on the topic of power. When we hear the word power, we might think of battery power, or the power of a horse, or the horsepower of a car, or the power of an Olympic weightlifter. But what exactly is power? In physics, power has a very specific meaning. Power is the rate at which energy is transferred, or as the transfer of energy and the doing of work are the same thing, the rate at which work is done. The equation for power looks like this: P equals E over T, where P is the power in watts, W, E is the energy transferred in joules, and T is the time taken in seconds. A second version of this equation looks like this: P equals W over T, where W is the work done in joules. From these equations, we can see that a power of 1 watt is equal to a transfer of 1 joule of energy per second, or to the doing of 1 joule of work per second. In calculations, these conversions might be useful. As we saw previously, kilo means 1000 and mega means million, so 1 kilowatt equals 1000 watts and 1 megawatt equals 1,000,000 watts. Have a look at these two cranes as they lift the same load. Which is more powerful? The one on the right, of course, because the rate at which it's transferring energy to or doing work on the load is greater. It's able to lift the load more quickly. Let's go through a few examples now. A really easy one to start us off. Here, we can see that the battery is transferring 3 kilojoules or 3000 joules of energy to the bulb. The amount of time taken is 20 minutes, so to convert to seconds we just multiply by 60, which gives 1200 seconds. From there, using our equation, power equals energy divided by time, and subbing in 3000 divided by 1200, which gives an answer of 2.5 watts, or 2.5 joules of energy per second. Let's build things up now with example 2. As you can see, the crane is lifting a load of mass 1200 kilograms through a vertical distance of 10 meters in a time of 40 seconds, and in part A, we need to work out the amount of gravitational potential energy which the crane transfers to the load, so let's give it a go. Remembering our equation, we have EP equals mgh, and subbing in that becomes 1200 times 9.8 times 10 to give an answer of 117,600 joules. In part B, when we say that the crane was 100% efficient, what we mean is that all of the energy which it supplied was converted to the GPE of the load. None was converted into other forms along the way. That makes our calculation really straightforward. We again use power equals energy over time, and subbing in that becomes 117,600 joules divided by 40 seconds to give an answer of 2,940 watts, or in kilowatts, 2.94 kilowatts. The first part of example 3 is very similar. The only real difference here is that the mass is in grams this time, and the change in height is in centimeters. Again, using our equation for gravitational potential energy, we have EP equals mgh, and subbing in that becomes 0.4 kilograms times 9.8 times 0.5 meters to give an answer of 1.96 joules. Part B now. Here, we're told that the power is 0.4 watts while the load is being lifted. To work out the amount of time taken, we just rearrange our power equation to give T equals E divided by P. Then subbing in, we have 1.96 joules from the previous part divided by 0.4 watts to give a time of 4.9 seconds. Ain't physics sweet? The last of these is a bit trickier. Why don't you pause the video here and see if you can give it a go? As you can see, the plane is accelerating from 150 to 200 meters per second in a time of 10 seconds. To work out the increase in the kinetic energy of the plane during this time, we just have to work out the initial and final kinetic energies and then calculate the difference. To work out the initial kinetic energy, we use our equation half mv squared, and then sub in that becomes a half times 10,000 times 150 squared, which gives an answer of 112,500,000 joules. Following the same steps, we find that our final kinetic energy is 200 million joules. So that means that our increase in kinetic energy is just the difference between these two numbers, which gives an answer of 87,500,000 joules. The key to part B is realizing that the increase in the kinetic energy of the plane is equal to the work done by its engines. From there, the rest of the solution is pretty straightforward. Starting off with our equation, power equals work done divided by time, and subbing in, we have 87,500,000 joules divided by 10 seconds, which gives a power of 8,750,000 watts, or in megawatts, 8.75 megawatts. In the last section of this video, we're going to look at the required practical activity for this part of the course, which is on how to measure the specific heat capacity of a material. Have a look at this equipment, which is being used to measure the specific heat capacity of the material which this cylinder is made from. We know that the equation for a specific heat capacity is C equals delta E divided by m delta theta. So to calculate the specific heat capacity of the material, we need to measure the amount of heat energy supplied to it, its mass, and its change in temperature. You can see that the heater which has been placed into the cylinder is connected to the main supply via a joule meter. As the name suggests, this device allows us to measure the amount of electrical energy which has been supplied to the heater. Let's have a look through this example now to see how this works. Our equation again is delta E equals mc delta theta, which we rearrange to give C equals delta E divided by m delta theta. Here, we can see that the amount of energy transferred to the steel was 7,840 joules, its mass was 0.4 kilograms, and its increase in temperature was 40 degrees Celsius, so that gives a value for its specific heat capacity of 490 joules per kilogram per degree Celsius. We can also carry out this experiment by using a wattmeter and stopwatch in place of a joule meter, because power equals energy over time, energy equals power times time, so that means that our specific heat capacity equation can be rewritten like this. Have a look through this second example. Our equation again was PT equals mc delta theta. Rearranging to make C the subject, we have C equals PT over m delta theta, and subbing in 0.6 kilowatts is 600 watts times 30 over 0.5 times 30, which gives a final answer of 1200 joules per kilogram per degree Celsius. Just a little extra point here. As you can see, the value we measured for the specific heat capacity of aluminium was 1200, but the actual value is lower at 900 joules per kilogram per degree Celsius. So why were we so far out? To answer that, let's think carefully about exactly what it was that we were measuring. The equation we used again was C equals PT over m delta theta. The mass of the cylinder would have been measured using a balance, and its change in temperature was measured using a thermometer, so both of these values should have been fairly accurate. That means that the problem must have been with our measurement of the amount of energy which the cylinder received. We assumed that all of the energy which was supplied to the heater was transferred directly to the cylinder, but in reality, some of this energy would have been transferred to the surroundings. In other words, the top line of our equation was an overestimate, which is why our value for C was too high. To get a more accurate value using this method, we could have insulated the cylinder, which would have reduced the heat loss to the surroundings. You can actually do this experiment even if you don't have access to a wattmeter or a joule meter. What you have to do is to connect this circuit with an ammeter in series with the heater to measure the current flowing through it, and a voltmeter in parallel to measure the PD across it. When we get to the electricity section, we'll see that the equation for the electrical power transferred to a component looks like this. P equals IV, where I is the current through and V is the PD across the component. That means that the electrical energy transferred, which is just power times time, becomes IVT. That means that for this experiment, our specific heat capacity equation ends up looking like this. That brings us to the end of this video on the topic of power. Thanks for watching, and have a go at some of the exam style questions.